Hello, Mr. Long. This is FRQ number 2. So in this scenario, we have a hanging block M attached to a sliding block S. And then part A asks us to draw, label a free body diagram for each block. Okay, so part A. So for block S, the forces that are acting on it is Fn, Fg, and T. And then for block H, we have just Fg of the block and T. Here, Fg is greater than T since the block is going to be going down. All right, part B asks us to derive an expression for the acceleration A of the hanging block H in terms of capital M and G. So I would look at the system like the two blocks as a system. So we have net force system is equal to mass H plus mass S times A, but net force of the system is also equal to mg of the block H, and just that because that's like the only force being applied to it, looking at it as a system. So we can equal these two together. G is equal to mh plus ms times A. And here we would just isolate for A by just dividing the two masses over. So it'd be mh times g all over mh plus ms is equal to A. And that is the acceleration for block H. And we can do using the system because they will have the same acceleration, both blocks. So yeah. Okay, C, and also here, we know that mh is equal to lowercase m and ms is equal to capital M. So we will just replace mh and ms in the equation. So it'd be lowercase m times g all over lowercase m plus capital M is equal to A. Okay, part C asks us to derive an expression for the tension T in the string connecting the blocks in terms of M, G, and A. Okay, so here I will just look at block H. So net force of block H is equal to mh times A, which is also equal to lowercase m A. Net force of each block is also equal to mhg, or I should rather say fgh minus t, which also equals to mhg, which also equals to lowercase m times g, forgot minus t, which is equal to lowercase mg minus t. And then I would just equal the two net forces each other. So it'd be mg minus t is equal to ma. And then to solve for t, I would just add the t over and minus the ma over. So it'd be mg minus ma is equal to t. And then here I can factor an m. So it'd be m times g minus a is equal to t. Okay, part D. Part D asks us if increasing the mass of sliding block M will have what effect on the acceleration A and tension T. So increasing the block of M or block S would essentially decrease the acceleration, because using the equation we found in part B, we found that mg is equal, or A is equal to lowercase mg divided by lowercase m plus capital M. So if we increase capital M, that means that you are dividing by a bigger number, and if you're dividing the same number by a bigger number, it just makes it smaller, so your A would be smaller. And then your T would increase, because in part C we solve for what T would equal, and T is equal to M times G minus A. And since your A decreases and your M and your lowercase m and your G are the same, your G is being subtracted by a smaller number. That means that that M will be multiplying by a bigger number, therefore T will be greater. Okay. Part E, that here in E, the scenario would change as well, or of the blocks. So now there's friction between the surface and block S. And then part E asks us to derive an expression for the acceleration of the system in terms of lowercase m, capital M, mu, and G. So then we do net force of the system is equal to FGH minus FK of block S. And then net force of the system is also equal to MH plus MS times A. And then this would also equal to lowercase m plus capital M times A. And then looking back at the FGH minus FKS, that would equal to MHG minus mu k, mu k FNS. And since on block S there's no like vertical force being applied to it, then Fn will equal to Fg, so this will make it equal to mhg minus mu k msg, which equals to lowercase mg minus mu k uppercase M and then G. And then from there we would equal the two equations together, so it would be the two net force systems together, so it would be lowercase m plus capital M A is equal to lowercase mg minus mu k uppercase M G. And then here, to solve for A, I'll just divide the masses over from the A, so it would be A is equal to mg minus mu k uppercase mg all over m plus m. And here, that is just what your A would equal to, or you can simplify further by factoring a G on the top. So A is equal to G times lowercase m minus mu k uppercase M divided by lowercase m plus capital M. Okay, that was E. Okay, F. F asks us to derive an expression for the tension in the string connecting the blocks. Okay, so I will look at the hanging block H. So then net force of H is equal to mh times A, which is equal to ma. And then net force of H is also equal to FGH minus T, which is equal to MHG minus T, which is also equal to lowercase mg minus T. Here I would equal the two net forces equations to each other, so it would be MA is equal to mg minus T. And then here, I would move T over to the other side, and move MA to the other side to isolate for T. So it'd be T is equal to mg minus ma. And then here I will replace a with what we found in part E, this equation. So then I will do that right now. So it would be T is equal to mg times, minus m times, copy? Yes, I did. Give me a second, sorry. Actually, I'll copy the one up in front without the g factored. Okay, copy this, and then, not zoom. Oopsies, sorry. Alright. And then here I would make it where both terms on the right side will have a common denominator. So I'll multiply mg by m plus m all over m plus m. So it'll be m plus m times mg divided by m plus m minus m divided by mg minus mu k mg all over m plus m. And then I would combine the terms, so it'll be t is equal to m plus m g minus m times mg minus mu, supposed to be capital, mu k capital M g all over m plus m. Okay. Here I would then distribute the mg to the parentheses and the negative m to the parentheses as well. So it'd be t is equal to m squared g plus case m g minus m squared g plus mu k uppercase m lowercase mg all over m plus m. And then here the m squared g and the minus into g will cancel out. So then you're left with t equaling mg minus, or not minus, plus mu k mg all over m plus capital M. And then here you can factor out uppercase m, lowercase mg on the top. So it would, t would equal to uppercase m mg times 1 plus mu k all over lowercase m plus capital M. Okay, and that is an equation for t. Okay. G. It says that with the presence of friction between the sliding block S and level surface, the tension T in the string between the block will. So the tension of the block would increase because if you think about it, the T here needs more. It's going to need more force to pull block S because there's going to be a force pulling it backwards now. So T would need to increase to account for that. And also, if you look here in the new T equation, friction would be added to it and it would increase T. Okay, so yeah, for G, with the tension, because of friction, tension would increase. Okay, H. Okay, H, the scenario once again changes. So then it's very similar to the previous scenario of friction, but now there is a block, lowercase m, that is in contact with block S. Okay, and part H asks us to draw and label a free body diagram for all the boxes. Okay, so for block S, we have Fn and Fg in the y axis, and they're equal because there's no other vertical force affecting the block. And there'd be, I should make that look more equal, but yeah, they're supposed to be equal in size. And then there's T pulling it to the right, and then there's going to be Fk of block S, and then there's going to be contact force between block S and M. Okay, so, and T will be greater than both FKS, or friction, and the contact force, because it's moving to the right and T is pulling it to the right. Okay, for the mini block M, the forces on it is also Fn, Fg of the block, and then there will be the contact force that's pointing it to the right. I should probably label this one. Okay, and then there'll also be friction of the block. And then the contact force would be greater than friction because it's moving to the right. And then for block H, there would just be Fg of block H and then T. And then Fg would be greater because it's going downwards. Okay. Part I. Okay, so we're given values for capital M, lowercase m, and mu, and we just need to calculate the acceleration of the system. So then we have net force of the system is equal to FGH minus friction of block S minus friction of the little block M. And we also know that F system is equal to mass H plus mass S plus little block m times A. And then that would equal to lowercase m plus capital case M plus lowercase m times A, which simplifies even further to 2 lowercase m plus capital M A. Right. And then here we will equal the two net forces equation together. 2 lowercase m plus capital M times A is equal to FGH minus FKS minus FK lowercase m. Okay. Here, FG H is equal to MHG, and then FKS is equal to mu K FNS, and then FKM is equal to mu K FNM. And then that would equal to lowercase mg minus mu K, and then Fn, S in the scenario is equal to FGS. So it'd be equal to FGS. And same with FNM minus mu K. FNM would equal to FGN times FG, not NM, sorry, M. And that would expand further to mg minus mu K capital Mg minus mu K lowercase mg. And then here, to solve for A, we would just divide 2 lowercase m plus capital M to both sides. So A is equal to mg minus mu K times mg minus mu K times mg divided by 2m plus m. And then here we'll just plug in the values. So a is equal to 3 times 9.8 minus 0.118 times 2 times 9.8 minus 0.18 times 3 divided by 2 times 3 plus 2. Let me look if I plug this in all correct. Yeah, and then this would equal to positive 2.57 meters per second squared. And here it'll be positive because we're going to take the line of motion to be positive. Okay, and that was I. All right, for J asks for calculate the tension of the string connecting the signing block S and hanging block H. And then here I would just look at the hanging block H. So then net force of block H is equal to FGH minus T, which equals to MH times G minus T, which equals to lowercase mg minus T. And then net force of FH is also equal to just MH times acceleration, and then which equals to just lowercase m times a. And then I would equal the two net forces equation to each other. So it'd be mg minus T is equal to ma, and then I would just add the T to both sides and minus ma to isolate for T. So it'd be mg minus ma is equal to T. And here I'll just plug in the values that were given in part I. So m is 3, G is 9.8 minus 3 times 2.57 is equal to T. And T would equal to 21.69 N, and then it'll be both positive and minus because for the string is like this, and then the tension is both gonna be like that. It's gonna be like up and down. It's like pointing at each other. So yeah, it'll be positive and minus. Okay. K. K asks to calculate the contact force F big M to lower M between the two blocks sliding on the rough surface. So then I will look at the small M block, so net force of little m is equal to the contact force between block S, or in this scenario, big M, because block S is equal to a big M, M to little m, minus friction of little m. We also know that net force of little m is equal to little m times A. And then looking back at the other equation we set up, we can expand that to make the friction equal to mu k and then little mg, because when we were finding acceleration, I think, or tension, we established that is what FKM is equal to. And here we equal the two net forces equation together. So F contact minus mu k mg is equal to ma. And then to solve for the contact force, I would just add mu k mg to both sides. It would be F m, or uppercase m, lowercase m, is equal to ma plus mu k mg. And here I would just plug in the values that were given to us in part I, so it'd be contact force is equal to 3 times 2.57 plus 0.18 times 3 times 9.8, which is equal to positive 13.002 n. And then the contact force would be positive because it's asking for m, big M to m, which is like, it would be like that, because big M is the one on the left and small m is the one on the right. So that's why it's positive. All right. Part L. Part L asks for the systems at rest determine the speed of the hanging block the instant before it strikes the ground. So then part L, we would use the common form. So Vf squared minus Vi squared is equal to 2AD. We're given that it starts from rest, so we can cross out Vi, and then we were given the height. The height is 20 meters from the diagram, and then we need to determine the speed. So we just isolate for Vi. So it'd be Va, and by doing that, to do that, we would just radicalize both sides. To go to radical 2AD, and then we would just plug in what we know. F is equal to radical 2 times 2.57 times 20. And then that would equal to 10.13 meters per second. Okay. Part M. Part M asks us to calculate the time required for the hanging block to cover the distance of 20. Okay. So here I would use our displacement, one of our displacement formulas, which is change in y is equal to 1/2 at squared plus VIT. But once again, the block starts at rest, so we can just cross that out. And then would a change in y will be 20 is equal to 1/2. And then A is 2.57 times t squared. And then here I'll just multiply by 2 to both sides. So it'll be 40 is equal to 2.57 t squared. Divide both sides by 2.57. So it'll be 15.56 is equal to t squared. And radicalize both sides. So it'll be t is equal to 3.94 seconds. All right. That was part M. Part N, the last part. It asked us to sketch a graph, a position versus time, velocity versus time, speed versus time, and acceleration versus time, and net force versus time, and then we'll take the direction of the motion as positive. Okay, so for the position time graph, so it'll be P as your y position as your y-axis and time as your x-axis, and then the shape of the graph would be like this. It'd be an upward parabola because since you're taking your line of motion to be positive, means that your graph should be your slope of the graph should be positive, and then it'd be concave up because acceleration in this case would be positive since you're taking the line of motion to be positive. All right, and then VT, the VT graph, with V being the y-axis and then T being the x-axis, it would just be a linear line like this. Same with the speed graph, speed versus time graph. Be like that. And then for your acceleration versus time graph, it would be a constant positive line with your A being that, and your A being your y-axis and your T being your time. Your T being your x-axis, sorry. And then for your F of T graph, your F will be your y-axis and your T will be your x-axis, and it would look the same as your acceleration graph. So then your acceleration here would be constant, and then since your acceleration is constant in this scenario, your force will also be constant, so that's why it's just a straight constant line, because net force is equal to MA, and then since A is the same, and M will stay the same in this case, it's just a straight line. And then your velocity is just a linear line because your acceleration is constant, so you're like accelerating in like a linear way. And then if you take the derivative of velocity, it'll just be constant. So that's why it'd be like that. And then your speed is the same as your velocity because you're you're not changing your direction at all because you're just taking the line of motion to be positive, so they'll just be the same. All right, so that was FRQ number two.